So hello everyone. My name is Natalia and I'm a security engineer at Isovalent. And for the last couple of years, I've been working together with the technical lead on Tetragon, both on production environments and on security use cases, like how a security team would use, for example, Tetragon. And then today I will just give a quick introduction on the part that we have open sourced during KubeCon. And then I will give a quick demo so more people can learn about it. So in the first section, I would like to talk about like what is Tetragon, how does it work, how it is leverages from the power of eBPF, what are actually the events that we are observing, and from all these events, which can be interested in, for example, for a security team, what do these events contain, and then basically how can you observe them via policy, and then in the end, I will show a quick demo on workload runtime visibility. So what is Tetragon? Tetragon is a combined runtime and network security observability and enforcement tool for applications that are running on cloud-native environments, for example, on Kubernetes, but it can run on standalone bare metal VMs. So it runs as a daemon set in case of Kubernetes, and then it runs as a simple container in case of like bare metal VMs. And then it can run on the top of every Linux operating system, and under the hood, it utilizes eBPF. So what does it mean exactly that it utilizes eBPF? So all the features and the logic that I will present today are done in kernel space. So Tetragon attaches to the kernel code bus by using eBPF to collect security observability data. So this functionality actually brings near real-time execution, minimal overhead, and then no disruption to the application. So for example, if you install Tetragon on your environment, you don't need to modify your application. It can continue running as it was before. And then secondly, by using these eBPF programs that Tetragon defines, you can collect the events exactly that you define from the kernel. So you are the one who actually filters what process, network, or file events you would like to collect. Or for example, what are the circumstances that you would like to see capabilities or namespace changes. So all of these events can be traced by policies. We call them tracing policies. And then these policies are dynamic. So you can load them anytime without even restarting the application or the pod. Even the pod doesn't even have to reach the ready state for a policy to take effect. And then with these tracing policies, we can observe like arbitrary events in the kernel. Right now, we have two main types which are supported, kprobes and trace points. And then with kprobes, you can observe arbitrary functions and then system calls. So all of these security events that we are observing, they are exported to user space as JSON events. And then these JSON events contain process and network information. And then it also contains Kubernetes identity-aware metadata. So Tetragon also enables Kubernetes identity awareness, both with eBPF programs and by bundling like an API watcher, which will pull the identity metadata from the Kubernetes API server, and then it will correlate the events which we observe actually in the kernel. So this identity actually includes pod names, and then the Kubernetes namespace, the container image IDs, and then labels. So basically, this is how we can trace, for example, the full life cycle of processes and the network sockets from start to finish from actually a Kubernetes workload. So now we have like a bunch of events, but like what are the events that can be translated into, for example, actionable signals that, for example, a security team would care about. So we came up with the idea of the 4 golden signals of container security observability, which will answer questions like, What are the processes that were executed during a workload lifecycle? What were the connections that were made? What were the files that were accessed? What were the capabilities and the namespaces that the process started with or maybe gained in the meanwhile? So for each of these signals, there can be a process-related event that Tetragon generates. An important note that these are just like a set of examples that we implemented so far in Tetragon. These are very representative and useful, but you are the one who have to pick the right set of trace points or like K-probes, which will match the events that you are looking for. So the first signal is to monitor like a process lifecycle. So for this, we observe like process exec and then process exit. These are internal events, and then process exec tells you how and when a process has started, and then basically process exit tells you how and when the process has terminated. So internally, the process exec event is hooking on the exec or fork system call, and then the process exit is using the exit system call. So these events contain process-related information like binary, command line argument, the UID context, parent process, working directory, capabilities that the process had started with, both effective, permissive, inherited, and also the namespaces that the process has had access to. And it also contains the Kubernetes identity-aware metadata. To monitor the network socket lifecycle and then like what connections were made, we can observe, for example, TCP connect, TCP send message, or TCP close kernel functions via K-probe hook points. So these will also generate process K-probe events. And these will tell you, like, for example, how a TCP socket was created and then how it was closed. And then they also contain information about the outbound connections like source IPs, destination IPs, and then also the process and the network related information that I mentioned before, as well as the Kubernetes identity aware metadata. So for monitoring file access, we are also using like K-probe hook points and then process K-probe events. So by using K-probes, these events are able to monitor arbitrary system calls and then file descriptors. And then basically with this, you will get the availability to get all the files that were opened or read or write through a process lifecycle. So as an example, for open and close, we use the fd install kernel function. And then for read and write, we use sysread and then syswrite system call. But these are just like a set of examples. You can define what kind of functions or system call you would like to trace. And then basically the first signal is the capability and namespace changes, which can be observed by also like a process K-probe event and then a system call. So for monitoring namespace changes, we right now observe the setns, unshare, and clone system calls. And then to detect capability changes, we currently check if there was a change in the process CRED struct inside the kernel. So how do we get these events? These events can be traced by, as I mentioned, by a policy. We call it tracing policy. So you can imagine that in a Kubernetes environment, it's a CRD, it's a custom resource definition. You can apply, and then you can apply it in a cluster. And then in bare metal environments, like in VMs, it's just like a configuration file. You can like load it into a container or like mount it into a container, and then Tetragon will automatically pick it up. So these policies, as I mentioned, able to trace arbitrary kernel events. Right now, two main ones are supported, K-probes and trace points. And then with K-probes, we can trace kernel functions and then system calls. So this is how, for example, we can observe sensitive system calls, for example, sysset UID and then sysmount. So you can monitor actually like gaining root access. You can also monitor, for example, sensitive file system mounts. And then by tracing kernel functions like fd install, you can also monitor like sensitive file opens. But if you apply a tracing policy, you get like a bunch of events. So we included kind of selectors. So with selectors, you can actually fine grain the events that you would like to get like in the kernel. So we have pit selectors. By a pit selectors, you can define if you would like to see host events only, or container events with init process or without the init process. We have argument selectors. Argument selectors defined like, for example, you would like to match or observe on an event with a certain argument from a system calls. For example, you would like to observe writes only to its password, or you would like to observe only writes to etc shadow. We have binary selectors. Binary selectors define if you would like to get events from a certain binary. We have capability selectors, like you can define, like you would like to get events coming from certain capabilities. Namespace selector, this defines if you would like to observe event which has access to a certain namespace. And then Tetragon like exports all this kind of event in like process exec and then the process kprobe events into a log file locally. And then we also have like a standard out container. And then basically the standard out container is just tailing this log file. If you are interested in tracing policies and like a couple of examples, you can go to the GitHub repository. We put a bunch of there. And then to make it like more visual, I included a quick demo as a final step. And then basically what we are trying to do here is to monitor sensitive file access from a process which has host network namespace access. So in this case, the file that we are going to monitor is like procnet-dev, and then this contains all the information about network adapters. So if we speak generally, accessing network devices in a container which has host network namespace access is a potential security threat. So as an example here can be, for example, running TCP dump on a network adapter of the physical device, for example, TCP dump as root. And then what TCP dump would do as a first step is just to open and check the contents of procnet-dev. So in this demo, I will show like how this open can be detected by Tetragon, and then we will see, for example, the other process related events as well that I described in the beginning. So I will just switch to the terminal. Let me know if it's big enough. So I will have two pods applied, one privileged and then one not privileged. We will see it up and running. And then we can actually check the content of procnet-dev, for example, from the unprivileged pod. So we can see here the loopback interface and also the ET0. And then we can also check the content from the privileged pod. So this would give us all the network adapters that we can see from the host. So let's take a look at the tracing policy that I'm going to apply, and then it will get like more visual. I'm not sure if it's like readable or not. So in this tracing policy, we are going to monitor a kernel function. It's called fd install. So basically, it looks when a file descriptor gets installed, and then it's called every time when a file is opened. So we can see here that we are going to monitor a file, and then we are going to match an argument which ends with netdev. So in this case, like procnet-dev, for example, and then in the namespace selector, we are going to match on processes which has host network namespace access. So I will just apply this policy. All right. And then I'm going to delete the privileged pod and then start it again. And then we will see the observability events via CLI. I just wanted to show it as well because it's really visual. And then it used to be a good demo. So on the second terminal in the bottom, I'm going to actually monitor this like standard out container that I mentioned before, which tells this log file where we are exporting the events. And then I'm going to use a CLI, which will monitor the processes or these events from the privileged pod. All right, we see that it's exited. These are from the previous delete. And then I will just apply the privileged pod. So the privileged pod will be an Nginx container, which is listening on localhost port 80. So as we can see already the privileged pod start with capsysadmin, and then basically we can see also some processes related to the Nginx container. We can also see like port 80 and then some configuration file read. So what I'm going to do, I will just exec into the privileged pod container. And then here we can actually see the bash execution. And then if we take a look at, these are the Kubernetes identity aware metadata. So for example, here you could see the default namespace, the container name. This is basically the binary. These are the arguments. And then basically these are the capabilities. And then this is basically the process type. So in this case, it was exec, and in this case, it was exit. So let's just read again the procnet file. And then if we zoom in, you could actually see the open on the proc some number netdev file with the capabilities capsysadmin coming from the pincat process, from the default namespace, from the privileged pod. And then we can see also that the process exited with an exit signal, exit code 0, so the read was actually successful. So that's the demo that I had in mind. And then let me know if you have any questions. And then let me just switch back to the slides. And then I would like to say thank you also on the behalf of the Tetragon team, because like a lot of engineering work is behind like all of this.
Cool, thank you, Natalia. That was a really interesting demo. It's actually the first time I've seen Tetragon in action, so it was really fun for me. Yeah. We have a couple of questions from the audience. The first one you answered in the chat, but I just want to do it in case anybody misses it. Do you reckon I'll be able to run Tetragon and Rancher desktop? Sounds like a silly question, but I was wondering if it's platform agnostic or only limited by the kernel version.
All right, where is this question?
It's in the chat. I can read out your answer too if you want.
Yeah, so it's basically the only requirement we have is the BTF metadata file. So it contains like debug symbols, the kernel debug symbols. So that's how Tetragon knows like how to structure and create these kind of events and how to program the BPF programs. So if the base kernel has BTF support, that should work automatically, or we need this like BTF metadata file in a place where Tetragon can read it. So there were customers who were interested in Rancher desktop because they were using M1 Max, so it should be possible.
Cool, thank you. The next one is from Gary. Is Tetragon supported in a cluster mesh architecture?
Yeah, so right now, interesting question. So right now, it runs as a daemon set. So the log file that you could see and all the events is like per node. So we would need kind of like a relay. We are working on it at the moment, where you could, for example, correlate events from from multiple clusters. But yeah, should be possible.
Cool, thank you. And then the last one, also from you again. Could Tetragon help out with monitoring activity within virtual machines, but from the hypervisor's perspective? So without an agent in the virtual machine, he's like, yeah, I know it's a weird use case.
So you would mean like kind of a Docker in Docker? Within a virtual machine. Yeah, I can follow up with the team.
I could jump in there quickly. So if you have, as soon as we start talking about a hypervisor, we're talking about a host machine that has its own kernel, and then guest operating systems that run within the hypervisor that have their own kernel. Mm-hmm. So eBPF instruments a kernel. The outer kernel doesn't, if we're talking about sort of true virtualization, the outer kernel doesn't have access into the guest OS kernel data structures. So I don't think you could just instrument the host machine and get guest virtual machine information. I think you would need to instrument the kernel in each guest.
That's not possible.
Okay, cool. Thanks for sharing, Natália. I guess now with the 6 minutes